Electric current. In this lesson, we shall learn about electric current. Electrons of different types of atoms have different degrees of freedom to move around. In some metals, the outermost electrons in the atoms are loosely bound, allowing them to leave their respective atoms and float around in the space between adjacent atoms. These electrons are called free electrons. Electrical conductivity involves the flow of free electrons through a solid body. Conductors are materials that allow electrons to flow freely from particle to particle. They permit charge transfer through the free movement of electrons. Example: copper, silver, aluminium. Insulators are materials that do not allow the free flow of electrons from one atom to the other. They have tightly bound electrons that are not shared easily by neighboring atoms. Example: rubber and wood. The direction of electric current is in the direction of the movement of positive charge and is always opposite to the direction of the flow of electrons. Earlier, when electrons were not discovered, the direction of current was considered to be the same as the direction of the positive charges. Later, when electrons were discovered, it was found that the movement of electrons is in a direction opposite to that of then defined current direction. This is the reason why the direction of the conventional current is opposite to that of the flow of electrons. Electric current means the rate of flow of an electric charge. It is constituted by the flow of positive charge. The net quantity of an electric charge flowing through any cross-section of a conductor is defined as electric current. If 1 coulomb of electric charge passes through a conductor in 1 second, an electric current of 1 ampere is said to flow through the conductor. The SI unit of electric current is coulomb per second. It is also represented in ampere. If the number of electrons passing through the cross-section of a conductor in time t equals to n, then the quantity of charge passing through the cross-section will be n multiplied by E. Replacing the values in the equation, I is equal to Q upon T, we get I is equal to N multiplied by E upon T. Question: if an electric bulb burns on 0.5 ampere current for 1 hour, how much electric charge will pass through it? How many electrons will pass through it? Given, elementary charge is equal to 1.6 into 10 raised to minus 19 coulomb. Solution: given current I is equal to 0.5 ampere, time t is equal to 1 hour equal to 3600 seconds. We know I is equal to Q upon T, or Q is equal to I into T. We get Q equal to 0.5 into 3600, which is equal to 1800 coulomb. So, electric charge passing through the bulb is 1800 coulomb. From the equation Q is equal to NE, replacing the values, we have N is equal to Q upon E. So, N is equal to 1800 upon 1.6 multiplied by 10 to the power minus 19, which is equal to 1125 multiplied by 10 to the power 19, equal to 1.125 multiplied by 10 to the power 22. So, the number of electrons passing through the bulb equal to 1.125 multiplied by 10 to the power 22. Question. While connecting a torch with a battery, an electric current of 64 milliampere flows through the bulb. If this torch glows for 10 minutes, how many electrons will pass through the bulb? Charge of electron E equal to 1.6 into 10 raised to minus 19 coulomb. Solution. Given current I is equal to 64 milliampere equal to 64 into 10 to the power minus 3 ampere. Time T equal to 10 into 60 equal to 600 seconds. E is equal to 1.6 into 10 to the power minus 19 coulomb. Electric current I equal to Ne upon T. Number of electrons N is equal to I into T upon E. N is equal to 64 into 10 raised to minus 3 into 10 into 60 upon 1.6 into 10 raised to minus 19 equal to 24,000 into 10 raised to 16. N is equal to 24 into 10 raised to 19 electrons.